Imagine holding the future in your hands, a device operating on principles that challenge our everyday understanding of reality. Now, rewind less than a century to a time when the cutting edge of computation involved fragile glass tubes, glowing hot, filling entire rooms just to perform calculations we now do instantly. How did humanity make such a monumental leap? How did we journey from the simple on-off switch of a vacuum tube towards harnessing the bizarre, powerful rules of quantum mechanics? This isn't just a story of gadgets getting smaller and faster. It's a profound narrative of human ingenuity, relentlessly pushing the boundaries of science and engineering, unlocking new layers of physical reality to build ever more powerful tools. This is the story of from vacuum tubes to quantum computing, the evolution of technology. Today, the technological descendants of those early electronic sparks underpin almost everything we do. How we communicate across the globe in an instant, how we design life-saving medicines, explore distant planets, and even how we entertain ourselves. The relentless drive towards miniaturization and increased processing power hasn't just changed our tools. It has fundamentally reshaped our world and expanded our potential within it. Understanding this incredible evolutionary path is key to grasping the forces driving our present and shaping our collective future. Join us as we embark on this remarkable journey through technological time. We'll begin in the era of the glowing vacuum tube, the dawn of electronics. We'll witness the solid-state revolution sparked by the transistor and the integrated circuit, explore the digital explosion powered by the microprocessor, and finally, peer into the strange, exciting, and potentially world-changing future promised by quantum computing. We'll uncover the pivotal breakthroughs, the fundamental scientific principles, and the visionary minds that propelled this relentless technological ascent. Prepare to witness the evolution that defines our modern age and hints at an even more extraordinary tomorrow. Our journey into the evolution of technology begins not with a bang, but with a spark, the gradual, painstaking unraveling of the mysteries of electricity itself. Before the vacuum tube ignited the electronic age, before complex computations happened in fractions of a second, the world operated at a fundamentally different rhythm, constrained by the limits of mechanics and the speed of human action. Communication across distances was a marvel achieved through wires or the slow transit of physical mail. Intricate calculations, essential for science and engineering, relied on ingenious but cumbersome mechanical devices or teams of human computers. Industry hummed to the tune of steam engines and elaborate clockwork, while the 19th century saw incredible mechanical progress. The tools available lacked the near instantaneous speed, the precise control, and crucially, the power of amplification needed for the next great technological leap. The potential, however, was latent in the very fabric of nature. Throughout the 18th and 19th centuries, brilliant minds like Benjamin Franklin, Alessandro Volta, Michael Faraday, Hans Christian Ørsted, and James Clerk Maxwell dedicated themselves to understanding the elusive forces of electricity and magnetism. They weren't necessarily envisioning global data networks or quantum bits. They were driven by fundamental scientific curiosity, yet their discoveries, generating stable electric currents, understanding the relationship between electricity and magnetism, formulating the laws of electromagnetism, laid the essential, theoretical groundwork upon which all subsequent electronic technology would be built. The first practical applications demonstrating the power of controlled electricity emerged in communication. Samuel Morse's telegraph, operational from the 1840s, used electrical pulses traveling through wires to transmit coded messages faster than any messenger could travel. Alexander Graham Bell's telephone, patented in 1876, achieved the even more remarkable feat of transmitting the human voice electrically. In the late 1880s, Heinrich Hertz experimentally confirmed the existence of the electromagnetic waves predicted by Maxwell's equations, paving the way for wireless communication. Guglielmo Marconi soon harnessed these radio waves, demonstrating wireless telegraphy across increasingly vast distances, shrinking the world in an unprecedented way. But a critical bottleneck persisted. It was the English physicist John Ambrose. Fleming, acting as a scientific advisor to Marconi's wireless company, who put the Edison effect to practical use. Seeking a better detector for weak radio signals, around 1904, he created a two-element vacuum tube containing only the heated filament, cathode, and the plate, anode. This Fleming valve acted as a diode, allowing current to flow in only one direction, thus rectifying the alternating current of radio waves into a detectable direct current. It was the first true vacuum tube, a vital component, but it couldn't amplify. The invention that truly unlocked the electronic age, providing the essential function of amplification and enabling high-speed switching, came just a few years later, from the American inventor Lee de Forest. In 1906, de Forest introduced a third element into the vacuum tube, a wire mesh or grid placed directly between the filament and the plate. He discovered that applying a small voltage signal to this grid could precisely control the much larger flow of electrons traveling from the filament to the plate. A weak signal on the grid could be faithfully reproduced as a much stronger signal at the plate. He called his invention the Audion. It was the first electronic amplifier, the triode, the fundamental building block of early electronics. Though the Audion was initially imperfect, and its operational principles weren't fully grasped even by its inventor for some time, its potential was revolutionary. It could boost faint radio and telephone signals, making reliable long-distance communication and broadcasting feasible. Crucially for the future of computing, it could also act as an extremely fast electronic switch, turning a current fully on or off far quicker than any mechanical device. The stage was now set. The fundamental laws of electricity were understood, and with the diode and the triode, humanity finally had the tools to precisely control and amplify electrical signals. The vacuum tube era was dawning, ready to power a technological revolution. The invention of the vacuum tube diode, and crucially the triode, provided the essential toolkit for the electronic age. Humanity now possessed the means to precisely control and amplify electrical currents at speeds far exceeding any mechanical device. The theoretical groundwork for electricity was established. The key components existed. Now, the challenge was to harness these components, particularly the triode's ability to act as both an amplifier and a high-speed switch, to build machines capable of complex tasks, especially the demanding task of automatic computation. This was the critical spark needed to transition from electrical communication to electronic information processing. While pioneers like Konrad Zuse in Germany were achieving remarkable feats with electromechanical relays, demonstrating programmable, automatic computation with machines like the Z3, the physical movement of mechanical switches inherently limited their ultimate speed. For calculations requiring immense speed, driven initially by scientific curiosity and soon by the urgent demands of global conflict, a purely electronic solution built upon the near-instantaneous switching capabilities of the vacuum tube was the necessary next step. One of the most significant, though for years overlooked advances in this direction occurred at Iowa State College in the United States. Professor John Vincent Atanasoff seeking a way to accelerate the tedious process of solving large systems of simultaneous linear equations for his physics students, conceived of an electronic digital calculator. Working closely with his exceptionally talented graduate student Clifford Berry, he designed and built the Atanasoff-Berry computer, or ABC, between 1937 and 1942. The ABC was groundbreaking in its architecture and its reliance on electronics. For logic operations, instead of relays, it employed approximately 300 vacuum tubes acting as digital switches. It performed calculations using binary arithmetic, recognizing the efficiency of representing numbers with just two states, on-off, perfectly suited to electronic switching. Furthermore, it featured an innovative form of dynamic memory using capacitors mounted on rotating drums, which needed to be periodically refreshed, a concept known as regenerative memory. While the ABC was purpose-built for solving linear equations and lacked the full programmability envisioned by Babbage or implemented by Zeus, it stands as a landmark achievement, arguably the first machine to incorporate electronic logic circuits. Binary arithmetic and regenerative memory, all key concepts in modern computing, it was tangible proof that electronic computation was feasible. However, the path towards large-scale electronic machines was fraught with immense practical difficulties. Vacuum tubes, the core components, were a double-edged sword. They offered unprecedented speed, but they were also relatively fragile glass. Bulbs, sensitive to shock and vibration. They generated considerable heat, requiring sophisticated cooling systems to prevent overheating and failure. They consumed significant amounts of electrical power, making large installations expensive to run. Perhaps most critically, individual tubes had a limited lifespan and could burn out unpredictably. Building a machine containing hundreds, let alone thousands of these components, and expecting them all to function reliably for extended periods, was an engineering challenge of the highest order. Early pioneers faced not only these technical hurdles, but also frequent skepticism and difficulties securing funding for such ambitious, unproven projects. Despite these obstacles, the lure of electronic speed proved irresistible, particularly as World War II engulfed the globe. The demands of warfare, calculating artillery trajectories, breaking sophisticated enemy codes, designing complex weaponry, required computational power far beyond existing capabilities. This wartime urgency provided both the motivation and, crucially, the resources needed to attempt electronic computing on a previously unimaginable scale. In Britain, the top-secret code-breaking efforts at Bletchley Park led to the development of the Colossus machines designed primarily by Tommy Flowers. To crack the German Lorenz cipher, Colossus utilized around 1,500 vacuum tubes, later expanded to 2,400 in the Mark II version, to perform complex logical operations on encrypted messages read from punched paper tape at high speed. While highly specialized for cryptanalysis, Colossus powerfully demonstrated the effectiveness of large-scale electronic circuits for information processing under intense pressure. Across the Atlantic, the U.S. Army funded the ENIAC project at the University of Pennsylvania's Moore School. Led by John Mauchly and J. Presper Eckert, ENIAC, Electronic Numerical Integrator and Computer, was designed primarily for calculating ballistic firing tables. Unveiled in 1946, it was a true electronic giant, containing over 17,000 vacuum tubes and consuming enough power to light a small town. Programming it involved manually setting thousands of switches and replugging cables, a laborious process. But its computational speed, performing additions in microseconds, multiplications in milliseconds, was simply staggering, thousands of times faster than its electromechanical predecessors. ENIAC's public demonstration cemented the vacuum. Tube's role as the key component for high-speed computation and captured the public imagination, heralding the arrival of the giant brain. Thus, The spark of the electronic age was ignited through these pioneering efforts. The core innovation was the successful application of the vacuum tube as a high-speed electronic switch, enabling the construction of circuits capable of performing logical operations and arithmetic far faster than any previous technology. Overcoming the significant challenges of heat, power, and reliability associated with large numbers of tubes required immense engineering skill. Machines like the ABC, Colossus, and ENIAC, though differing in architecture and purpose, collectively represented the crucial transition from electromechanical concepts to electronic reality, setting the stage for the next great leap: the stored program computer. The initial sparks of electronic computation, embodied in machines like the ABC, Colossus, and the giant ENIAC, proved the immense speed advantage of vacuum tubes over mechanical or electromechanical methods. But these pioneering machines, particularly ENIAC, with its laborious plugboard programming, highlighted the next major bottleneck: feeding instructions quickly enough to keep the electronic circuits busy. The stage was set for the next great leap, the stored program concept, which would define the very architecture of computing for decades to come, marking the true beginning of the computer's powerful ascent. The limitations of programming. ENIAC, by physically rewiring it, were obvious to its creators and observers, like the brilliant mathematician John von Neumann. The revolutionary idea, formalized in von Neumann's influential 1945 first draft of a report on the EDVAC, was to store the computer's operating instructions, the program itself, in the same electronic memory used to store the data it was processing. This meant the computer could access and execute instructions at electronic speeds, limited only by memory access times, not by slow paper tape readers or manual setup. Furthermore, it opened the door for programs to modify themselves or other programs, enabling far greater flexibility and paving the way for software development as we know it. This von Neumann architecture, though its sole attribution to him is debated, as Mauchly, Eckert, and others contributed significantly to the discussions, became the fundamental blueprint for virtually all computers that followed. Implementing this stored program architecture became the primary goal of computer development in the immediate post-war years. A global race of sorts ensued. In the UK, the Manchester Baby, small-scale experimental machine, etched its place in history by successfully running the world's first stored program in June 1948. This was quickly followed by the more developed Manchester Mark I and the influential IDISAX, electronic delay storage automatic calculator at Cambridge University, which provided a computing service to researchers. In the US, development continued on the EDVAC itself, while other projects based on the von Neumann architecture, like the IAS computer built at Princeton's Institute for Advanced Study, pushed the frontiers of design and application. This era also witnessed the crucial birth of the commercial computer industry. Mauchly and Eckert, the minds behind ENIAC, left academia to form the Eckert-Mauchly Computer Corporation, aiming to bring electronic computing to a wider market. Their landmark achievement was UNIVAC I, the Universal Automatic Computer. Delivered to the US Census Bureau in 1951 and subsequently sold to businesses, UNIVAC I became the first commercially mass-produced electronic digital computer in the United States. Its famous and accurate prediction of Dwight D. Eisenhower's landslide victory in the 1952 presidential election, broadcast live on television, dramatically brought the power and potential of computing into the public consciousness. UNIVAC's use of magnetic tape for high-speed data input and output was also a significant advance over the cumbersome punched cards used by many earlier systems. IBM, initially cautious under its founder Thomas Watson Sr., soon recognized the unstoppable momentum of electronic computing. Driven by the vision of Thomas Watson Jr., IBM entered the market decisively and strategically. The 701 defense calculator, released in 1952 primarily for scientific and military computations, was quickly followed by the 702, designed for business data processing. IBM invested heavily not only in hardware but also in reliability and support. A key technological advance rapidly adopted during this period was magnetic core memory, replacing earlier, often volatile or slow memory technologies like mercury delay lines or Williams tubes based on CRT persistence. Core memory used tiny, durable ferrite rings strung on a grid of wires. Each core could store one bit of information by being magnetized in one of two directions. It was relatively fast, non-volatile, retaining data even when power was off, and became the dominant form of computer main memory for nearly 2 decades, enabling larger, faster, and significantly more reliable first-generation systems. With functional stored program computers becoming available, the challenge shifted towards usability. Programming directly in binary machine code was excruciatingly complex and error-prone. Visionaries like Grace Hopper, a key figure in early UNIVAC programming, championed the development of compilers, sophisticated programs that could translate instructions written in more human-readable, high-level languages into the machine code the computer understood. Her pioneering work on the A0 system compiler paved the way for future language development. Recognizing the need for scientists and engineers to program complex calculations more easily, IBM's John Backus led the team that developed Fortran, formula translation, in the mid-1950s. Fortran became the first widely adopted high-level programming language, dramatically increasing programmer productivity in technical fields. Similarly, the growing use of computers for business data processing led to the collaborative development of COBOL, Common Business-Oriented Language, around 1959, heavily influenced by Hopper's language design ideas, which became the standard for business applications for decades. Despite these crucial software advances, first-generation computers remained colossal, power-hungry machines, reliant on thousands of vacuum tubes that frequently failed, restricting their use to only the largest organizations. The fundamental physical limitation remained the vacuum tube, the revolution that would truly shrink the computer and make it vastly more reliable came from solid-state physics, the transistor. Invented at Bell Labs in 1947 by John Bardeen, Walter Brattain, and William Shockley, who would share the Nobel Prize for the work, the transistor could perform the same electronic switching and amplifying functions as a vacuum tube. However, it was fabricated from semiconductor materials, making it incredibly small, incredibly durable, consuming minuscule amounts of power, generating very little heat, and offering vastly improved reliability. As manufacturing techniques matured through the 1950s, transistors became ready to supplant the vacuum tube at the heart of computer design. This transition marked the second generation of computers. Machines appearing in the late 1950s and early 1960s, such as the IBM 7090, a transistorized successor to the vacuum tube 709, and its powerful follow-on, the 7094, the Philco Transac S2000, an early transistorized machine, the Control Data Corporation, CDC, 1604, designed by Seymour Cray, and later UNIVAC models, leveraged the transistor's advantages. They offered significant leaps in processing speed and computational power, packed into smaller physical footprints, though still typically requiring large, air-conditioned rooms, and crucially, they were far more reliable and required less maintenance than their predecessors. This enhanced reliability and performance broadened the appeal and economic viability of computers for a wider array of scientific research and, importantly, complex business operations like inventory management, payroll, and accounting. solidifying the era of the mainframe computer within large corporations and government agencies. IBM, with its strong technological base, extensive sales force, and focus on business solutions, particularly flourished, establishing a dominant position in the global mainframe market. Just as the transistorized second generation hit its stride, the next wave of miniaturization was already breaking. The integrated circuit, IC, colloquially known as the microchip, developed independently and almost simultaneously around 1958-59 by Jack Kilby at Texas Instruments, who created a hybrid circuit, and Robert Noyce at Fairchild Semiconductor, who developed the monolithic integrated circuit manufacturing process. The IC was a paradigm shift. Instead of wiring individual transistors together, Noyce's approach allowed multiple transistors, resistors, capacitors, and their interconnections to be fabricated simultaneously on a single monolithic piece of semiconductor material, usually silicon. This enabled manufacturing efficiencies, dramatic reductions in size and cost, and further improvements in speed due to shorter connection paths and reliability, fewer solder joints to fail. Computers designed using integrated circuits defined the third generation. IBM again made a defining move with its announcement of the System 360 family in 1964. This was arguably the most influential computer line ever introduced. Its core innovation was not just the use of advanced components, initially hybrid circuits called solid logic technology, later monolithic ICs, but its concept of a unified, scalable architecture. System 360 comprised a range of models with different processing speeds and memory capacities, all capable of running the same software without modification. This upward compatibility was revolutionary, protecting customers' massive investments in software as their hardware needs grew. It required an immense $5 billion development effort from IBM, a bet the company gamble, but its success was staggering. System 360 standardized many aspects of computing, including the 8-bit byte as a fundamental unit of data, and cemented IBM's dominance for over a decade. However, the very technology that powered the System 360 also enabled a challenge to the mainframe's dominance. The significantly lower cost and smaller size, made possible by integrated circuits, allowed for the creation of an entirely new category, the mini-computer. Digital Equipment Corporation, DEC, founded by MIT Lincoln Laboratory engineers Ken Olsen and Harlan Anderson, pioneered this market. Their PDP-8, launched in 1965 at a price point below $20,000, a tiny fraction of a mainframe's cost, was a runaway success. It was small enough to be used by a single department, research lab, or even integrated into industrial control systems. Crucially, mini-computers like the PDP-8 and DEC's later hugely influential 16-bit PDP-11 fostered interactive computing. Users could sit at a terminal, often a teletype machine initially, and interact directly with the computer in real time, a stark contrast to the detached batch processing workflow common with mainframes. This accessibility spurred innovation. In operating systems like Unix, developed at Bell Labs on a PDP-7, programming languages designed for ease of use, like BASIC, created at Dartmouth College, and fostered the early hacker culture focused on exploring the capabilities of these more accessible machines. Fierce competition from companies like Data General, with its Nova mini-computer, further drove innovation and lowered prices in this rapidly expanding market. Throughout this period of rapid hardware advancement, the trend of exponential improvement became increasingly apparent. In 1965, Gordon Moore, then at Fairchild Semiconductor and later a co-founder of Intel, observed that the number of transistors that could be economically placed on an integrated circuit had been roughly doubling every year or two. He predicted this trend would continue. This observation, now famously known as Moore's Law, became both a description of historical progress and a powerful driver for the semiconductor industry, setting targets for relentless miniaturization and performance gains that held remarkably true for decades. The logical culmination of the integrated circuit revolution, driven by Moore's Law, arrived in 1971. Engineers at the young semiconductor company Intel, led by Federico Fagin, Marcian Hoff, and Stanley Mazur, achieved a monumental feat. They successfully integrated all the essential components of a computer's central processing unit, CPU, the arithmetic logic unit, control unit, registers, onto a single chip of silicon. This was the Intel 4004 microprocessor. Although initially designed for a Busicom calculator and limited in its capabilities, a 4-bit processor, its existence proved the principle. It was quickly followed by more powerful 8-bit microprocessors, including the Intel 8008 in 1972 and the significantly more capable Intel 8080 in 1974, along with competitors like the Motorola 6800. This single chip, the microprocessor, contained the very essence of a computer's brain. It held the key to making computers not just mini, but truly personal. In just 3 decades since the first electronic sparks flew in machines like ENIAC, the technological landscape had been utterly reshaped. The journey had progressed through distinct generations, defined by their core switching technology. From the heat and fragility of vacuum tubes, through the reliability and efficiency of transistors enabling mighty mainframes, to the incredible density of integrated circuits powering interactive mini-computers. And now, the microprocessor stood ready, poised to shrink computing power onto a single affordable chip, setting the stage for the most disruptive and democratizing phase of the evolution yet, the personal computer revolution. The invention of the microprocessor, successfully compressing the core logic of a computer's central processing unit onto a single silicon chip, was the crucial technological catalyst the world had been anticipating. It wasn't merely a continuation of the miniaturization trend seen with transistors and integrated circuits. It fundamentally altered the economics and accessibility of computing power. This breakthrough paved the way for the computer's great migration from the confines of large organizations and specialized laboratories directly into mainstream society, onto desktops, and into homes. The personal computing revolution was about to ignite. As we've explored in the specific history of computers, the initial sparks flew within the passionate electronics hobbyist community. The launch of the MIT's Altair 8800 in 1975, famously featured on the cover of Popular Electronics, was pivotal. Built around the powerful Intel 8080 microprocessor, the Altair, especially in its affordable kit form, democratized access to programmable hardware on an unprecedented scale. It unleashed a wave of grassroots enthusiasm. Computer clubs like the Homebrew Computer Club in Silicon Valley became hotbeds of innovation. Newsletters proliferated, and a vibrant community emerged, eager to build, share, and explore the potential of these new machines. Crucially, this era saw the birth of personal computer software, with Microsoft famously developing its BASIC interpreter specifically for the Altair, making the machine programmable by a much wider group than just hardware experts. However, for computing to truly reach the masses, it needed to move beyond kits requiring technical assembly. The watershed moment arrived in the late 1970s, particularly the landmark year of 1977, which saw the introduction of pre-assembled, user-friendly personal computers. The Trinity, the Apple II, the Commodore PET, and the Tandy TRS-80 brought computing out of the workshop and into living rooms, classrooms, and small businesses. The Apple II, driven by the engineering brilliance of Steve Wozniak and the marketing vision of Steve Jobs, captivated users with its color graphics, sound capabilities, and relatively approachable design. Its open architecture encouraged a thriving ecosystem of software and peripherals, and the arrival of VisiCalc, the first electronic spreadsheet, provided a compelling practical application, a killer app that drove adoption, particularly in business and education. Commodore's PETI offered a convenient all-in-one design, while Tandy's TRS-80 leveraged Radio Shack's vast retail network to make computers readily available across America. What fueled this sudden explosion? It was a perfect storm of converging factors. Moore's Law continued its relentless march, driving down the cost of essential components like microprocessors and memory chips. Manufacturing processes matured, enabling reliable mass production of complex electronic devices. Critically, software evolved. User-friendly programming languages like BASIC lowered the barrier to entry, while practical application software, like VisiCalc and early word processors, provided tangible benefits for everyday users, not just programmers. Furthermore, companies like Apple began to master the art of marketing personal computers, creating desire and demystifying the technology for a broader audience. The growth trajectory was explosive. From a few thousand hobbyist machines in the mid-70s, the personal computer market surged into millions of units sold annually by the early 1980s. This rapid expansion was further accelerated by the entry of the industry giant IBM. In 1981, the IBM personal computer, the IBM PC, instantly legitimized the personal computer for serious business use. By strategically using readily available components, including Intel microprocessors, and adopting an open architecture that encouraged third-party development, IBM inadvertently created a market standard. This spawned a massive industry of IBM-compatible clones running Microsoft's MS-DOS operating system, further driving down prices and expanding the user base exponentially. This mainstream adoption of personal computing triggered the first profound societal shifts directly attributable to the miniaturization of electronics that began with the transistor and IC. Word processing began displacing the typewriter, transforming how documents were created and edited. Spreadsheets revolutionized financial modeling and accounting for businesses of all sizes. Database software enabled efficient information management. Computer literacy emerged as an increasingly valuable skill. The nascent video game industry found a massive new platform in home computers, driving hardware sales and software innovation. Entirely new industries centered around personal computer software, hardware peripherals, magazines, training, and retail blossomed almost overnight. Although the truly interconnected world of the internet was still largely in the future, this era marked the decisive moment when the computational power unlocked by decades of electronic evolution finally became personal, accessible, and began its irreversible integration into the fabric of daily life. The personal computer revolution placed unprecedented computational power onto millions of desktops, transforming work and leisure. But the evolution of technology, driven by the relentless engine of Moore's Law and human ingenuity, was far from over. The late 20th and early 21st centuries witnessed further paradigm shifts, weaving electronic computation even more deeply and intimately into the fabric of global society, leading us into the complex contemporary era we inhabit today. Perhaps the single most defining development was the Internet's metamorphosis, from a specialized network into a ubiquitous global platform for communication, commerce, and information. Fueled by the creation of the World Wide Web by Tim Berners-Lee and the advent of user-friendly graphical web browsers in the early 1990s, the Internet became accessible to hundreds of millions, then billions. The subsequent dot-com boom and bust only paved the way for the rise of Web 2.0, characterized by social media giants like Facebook, Twitter, and YouTube, user-generated content, blogs, wikis, and interactive online services. This didn't just connect machines. It fundamentally rewired human connection, information access, political discourse, and economic activity on a planetary scale. Running parallel to, and increasingly converging with, the Internet's expansion was the mobile revolution. While early mobile phones existed, the launch of the Apple iPhone in 2007, followed swiftly by Google's Android operating system, marked a turning point. These weren't just phones. They were powerful, pocket-sized computers featuring intuitive touchscreen interfaces, sophisticated sensors, GPS, accelerometers, high-quality cameras, and constant connectivity. The explosion of mobile applications, or apps, transformed these devices into indispensable tools for navigation, social networking, mobile banking, photography, entertainment, and countless other aspects of daily life. Computing became truly personal, portable, context-aware, and perpetually online, further accelerating the digital transformation of society. Underpinning much of this always-on, data-intensive ecosystem is cloud computing. This paradigm shift involved moving data storage and heavy computational tasks away from individual end-user devices and onto vast, highly efficient, remote data centers operated by major technology companies like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform. The cloud enabled unprecedented scalability for internet services, allowed businesses to access powerful computing resources on demand without massive upfront investment, fueled the explosive growth of streaming media services like Netflix and Spotify, and popularized the software-as-a-service (SaaS) model, fundamentally changing how software is distributed and consumed. This era has also witnessed a dramatic resurgence and practical application of artificial intelligence, AI, and machine learning (ML). Decades of theoretical work finally bore fruit, propelled by three key factors: the availability of massive datasets, big data, generated by online activity, the immense processing power offered by cloud computing and specialized hardware, particularly graphics processing units or GPUs, pioneered by companies like NVIDIA, and significant advances in algorithms, especially in the field of deep learning. AI moved from research labs into tangible products and services, powering search engines, personalizing content recommendations, enabling sophisticated language translation, driving voice assistants like Siri and Alexa, improving medical image analysis, and making strides in complex areas like autonomous driving. The development and application of AI have become central pillars of the modern tech landscape. Beyond these dominant trends, the core electronic and computing technologies continue to diversify and specialize. Embedded systems integrated microprocessors into virtually every manufactured product imaginable, from cars containing dozens of processors managing engine control, safety systems, and infotainment, to smart home appliances, industrial machinery, and medical devices, collectively forming the sprawling Internet of Things, IoT. At the other extreme, supercomputing continued its relentless pursuit of raw processing power, with machines capable of performing quadrillions, petaflops, and now quintillions, exaflops of calculations per second, tackling grand scientific challenges. Wearable technology, like smartwatches and fitness trackers, brought computation even closer to the human body, monitoring health and providing instant notifications. And looking toward the next horizon, research into fundamentally different computing paradigms like quantum computing, aiming to leverage quantum mechanics for specific types of complex calculations. Neuromorphic computing, mimicking the brain's structure, and even optical computing using light instead of electrons, actively seeks the breakthroughs that could define the next era of technological evolution. The contemporary technological landscape is thus one of staggering complexity, scale, and integration. Billions of people wield powerful computing devices interconnected through global networks, generating data at an almost incomprehensible rate. The industry is characterized by powerful platform companies operating at a global scale, alongside highly specialized semiconductor manufacturers like TSMC, Intel, Samsung, and designers like ARM and NVIDIA who provide the fundamental hardware. Yet this pervasive technological integration brings forth critical challenges for the 21st century, navigating the complex issues of data privacy and digital surveillance, defending against increasingly sophisticated cybersecurity threats, combating the societal effects of misinformation amplified by online platforms, ensuring fairness and accountability through addressing algorithmic bias in AI systems, bridging the persistent digital divide to ensure equitable access, mitigating the significant environmental impact of electronic waste and data center energy consumption, and grappling with the profound ethical questions posed by ever more capable AI. The evolution continues, but its path forward is intertwined with these complex societal considerations. We've journeyed through an extraordinary technological landscape, tracing the path from the fragile glow of the first vacuum tubes controlling electrical currents, through the solid-state revolution of transistors and integrated circuits that packed unimaginable power onto minuscule chips, to the dawn of microprocessors, personal computing, global networks, and the burgeoning era of artificial intelligence. Standing now, looking back across this relentless cascade of innovation, we must ask, what is the true, lasting impact, the enduring legacy of this profound technological evolution? To fully appreciate the transformation, consider again the world. Before practical electronics took hold, a world where complex calculations were painstakingly slow. Long-distance communication was a marvel measured in hours or days, information was scarce and localized, and industries operated at the rhythm of mechanics and human labor. The contrast to our present reality could hardly be more stark. We now exist within a framework of instantaneous global communication, possess access to the vast majority of human knowledge via devices in our pockets, navigate economies driven by data flows and automated systems, and witness scientific discovery, accelerated by computational power that dwarfs anything conceivable a century ago. This isn't just change, it's a fundamental reshaping of the human experience. The long-term effects ripple through every domain of life. Science has been irrevocably altered, with computation emerging as a crucial third pillar alongside theory and experimentation. Complex simulations, modeling everything from climate change and galaxy formation to drug interactions and protein folding, drive discovery at an unprecedented pace. Global economies have been radically transformed. Entirely new industries built on software, digital services, and semiconductor manufacturing now dominate, while automation and data analytics continuously reshape traditional sectors, impacting productivity and the very nature of work. Culturally, the digital realm fostered by this technological evolution has spawned new forms of art, music, interactive entertainment, and global communities, fundamentally altering how we create, share experiences, and connect with one another across geographical boundaries. From healthcare diagnostics and personalized medicine to education delivery and logistical planning, virtually no significant aspect of modern civilization remains untouched. Perhaps the most profound legacy of this entire evolutionary chain, from vacuum tube to quantum bit, lies in its role as a foundational enabling platform. Each major technological leap didn't just improve upon the last, it unlocked entirely new possibilities. Vacuum tubes made electronic radio, television, and the first computers possible. Transistors enabled portable electronics, reliable mainframes, and the space race. Integrated circuits powered mini-computers, calculators, and paved the way for personal devices. The microprocessor democratized computing power, leading to the PC revolution. This cumulative progression forms the essential technological bedrock upon which subsequent revolutions, the internet, mobile communications, the AI explosion, advancements in biotechnology, material science, and countless other fields, are built. Therefore, the evolution from vacuum tubes towards the frontiers of quantum computing represents far more than a mere succession of faster, smaller components. It signifies a fundamental transformation in humanity's capacity to manipulate energy, process information, communicate ideas, model complexity, and ultimately understand and reshape our world. Much like the agricultural revolution shifted us from nomadic life, or the industrial revolution harnessed mechanical power, the electronic and digital revolution, born from these technological advancements, stands as a defining characteristic of the modern epoch, an ongoing transformation, whose ultimate consequences are still unfolding, but whose historical significance is already undeniable. Having traced the remarkable journey of technology's evolution from the first electronic sparks to the complex digital tapestry of today, the question inevitably arises: what comes next? The relentless pace of innovation, driven by scientific curiosity, engineering prowess, and economic imperatives, shows no signs of slowing. If the past century took us from vacuum tubes to powerful AI in our pockets, where might the next chapters of this technological saga lead us? At the absolute cutting edge, researchers are pushing into territories that challenge our fundamental understanding of computation and reality itself. Quantum computing remains a major frontier. While still largely experimental and facing significant hurdles in achieving stable, large-scale, error-corrected machines, progress continues. Harnessing quantum phenomena like superposition and entanglement, these machines hold the potential to revolutionize fields like materials science, drug discovery, cryptography, and complex system optimization by tackling problems currently far beyond the reach of any classical computer. Simultaneously, the quest for more powerful and efficient artificial intelligence continues unabated. Beyond refining today's increasingly sophisticated specialized AI, significant research focuses on the long-term, ambitious goal of artificial general intelligence, AGI. Machines possessing cognitive abilities comparable to humans. Alongside this, alternative computing architectures are being actively explored. Neuromorphic computing seeks to emulate the brain's low-power, parallel processing structure in silicon, while optical computing investigates using photons instead of electrons for potentially faster and more energy-efficient data manipulation. And some even explore the potential of biological computing. Looking at more predictable near-term trends, experts anticipate the even deeper and more seamless integration of specialized AI into our daily lives, enhancing productivity tools, enabling more personalized healthcare and education, powering increasingly autonomous systems, and creating more natural human-computer interactions. The Internet of Things, IoT, is expected to mature, connecting billions more devices and creating smarter, more responsive environments, though also raising significant security and privacy challenges. We are also likely to see continued advancements in brain-computer interfaces, BCIs, potentially offering new pathways for communication and control for those with disabilities, and perhaps eventually, new forms of human augmentation. Crucially, the imperative for sustainable or green computing will intensify, driving innovation in energy-efficient processors, data center design, and responsible electronics life cycles. Peering further into the speculative future, the possibilities become truly transformative and the questions more profound. What societal shifts would occur if practical, fault-tolerant quantum computers become widely accessible? What are the true implications, ethical, economic, existential, of achieving AGI? Will Moore's law, the engine of decades of progress, finally hit insurmountable physical barriers, or will new paradigms like 3D chip stacking or novel materials keep the exponential trend alive in new forms? The potential to reshape medicine, energy, communication, and perhaps even our understanding of consciousness itself is immense. This future trajectory, however, isn't fixed. It will be shaped by the scientific breakthroughs we make, the engineering challenges we overcome, the economic incentives we create, and critically, the ethical frameworks and societal choices we implement regarding these powerful emerging technologies. So the final questions turn to you. Which of these future technological frontiers most excites or perhaps concerns you? Do you foresee breakthroughs like widespread quantum computing or AGI happening in the next few decades? And ultimately, what role do you believe technology should play as our future continues to unfold? Share your thoughts, speculations, and hopes in the comments below. So, from the foundational glow of vacuum tubes that first harnessed electricity for complex tasks, through the transformative revolutions of the transistor, the integrated circuit, the microprocessor, and onto the very frontiers of quantum computing, we've charted a course through the relentless evolution of technology. It's a powerful reminder that human ingenuity constantly seeks to transcend limitations, reshaping our world in the process with each successive leap. Thank you sincerely for joining us on this exploration through the pivotal advancements that have defined our modern era and continue to shape our future. If this journey through technological history sparked your curiosity, please show your appreciation by hitting the like button and consider sharing this video with others who are fascinated by science, history, and innovation. We're genuinely interested in your perspective on what lies ahead. Please share your thoughts, predictions, and answers to our questions about the future from the previous section down in the comments below. And finally, to ensure you don't miss our future deep dives into the technologies that are shaping our world, make sure you subscribe to the channel and click the notification bell. Thanks again for watching.